Hi guys, welcome to ECE 385 Lab 4. In this video, I am going to show you an example SystemVerilog project using quarters. Before we get started, we have to go to the course wiki and download two files provided for us. One is the skeleton file for the 8-bit serial processor, which is an extension for the 4-bit logic processor that we built in Lab 3, but this one is just a SystemVerilog version. The other one is the skeleton files provided for the three adders that we're going to implement in Lab 4. Both of these are what we're going to implement in Lab 4. Then we go to the EDA tool called Quarters. We click on New Project Wizard. We click Next, and then we will name our project ECE 385, maybe Lab 4. Because it's a demo, I'll name it demo adder. And then we click on next. OK. It says select a different directory. Say no, we just want this. And we start from an empty project. So now we're going to add the files that we have just downloaded to our project. So I'll go to my G drive demo, adders, and add all the files. Yes, they're here, and I'll click next. Select the version that we're using. We're using the Cyclone 4E, and the device is at the bottom is end with 29C7. So next. So the simulation tool we use is the Model Sim Altera. Pay attention, it's kind of different from the Model Sim. Model Sim Altera comes with the quarters when you download it from the website. They're both free. And we're going to use SystemVerilog HDL. And then next. Yeah, that's it. So let's go to the file list and open up the top level entity. So basically, you can imagine a hardware as a black box, which is a module with some name, and it has got some input and output pins. So these are the pins that extends out of the black box that interacts with other modules or the whatever. Then down here we have internal logic declaration, which are the registers, wires, and stuff that we use inside a piece of hardware. And now we can see a procedural block. This is an always FF block. We also have always comp for combinational logic, always FF for sequential logic, because we can see this block will be triggered at a positive edge of the signal called clock, and which means at every positive edge of the clock signal, the following will happen. Down here, we see several instances of the modules that we're going to implement in this adder lab. So you can see the look ahead adder and the select adder are commented out because in this lab, we're going to compile one adder at a time. So we're going to basically repeat the same procedure 3 times when you're doing the demo. So now we're using the carry ripple adder, which I am going to implement in this demo. And down here we have hex driver instances. We have 1, 2, 3, 4, 5, 6, 7, 8 of them. So the hex drivers are the LEDs that can display numbers on the FPGA development board. Okay, by the way, on this board, as you can see here, the FPGA is only this square, this black square here. The whole board is called DE2115 development board or education board. We often call it the FPGA board, but really the FPGA is just that small piece. And down here you can see the hex displays, which can be driven by the hex driver. So now let's check our ripple adder module. So each module has a module, the name, input, output, as we can also see in the top level. By the way, top level includes all the module. you have in your design, but itself is also a module. It's a wrapper module, and we have an AND module to declare, okay, this module is AND. Why? Because you can put multiple modules in the same files. So we're gonna insert code here to implement a carry REPL adder. So in order to build the, I guess, all of the adders, we have to build the basic building block, which is called a full adder. So we're gonna type in module full adder here, okay, and we're gonna implement the full adder module. By the way, you can also check this out at the end of the lab manual, but I'm just gonna do here. So input X, input Y, because you can see a full adder has an input X, input Y, and input carry in. So input C in, right? And also the output. For some reason, if you don't put the keyword logic here, Quartus will complain when you're trying to compile this this project. So we're just going to put it here. So S, and then output logic C. Okay, so these are all 1-bit logics. 1-bit input, 1-bit output, 1-bit carry. So let's call this C out actually. So this is a 1-bit full adder. And also let's put the AND module here in case we forget. Okay. So next we're gonna define what's inside the module. We're gonna use the most fundamental syntax in SystemVerilog, which is called assign. Assign. So basically you can view assign as a piece of wire. And we're gonna assign the sum S to be equal to X. XOR, by the way, XOR is this hat symbol in SystemVerilog, and I guess in C as well. XOR with Y, XOR with the carry in, okay? And each line should end with a semicolon. Then we're gonna do assign the carry out to be equal to X and with Y, or with Y and with C in, or with C in and with X. Oops, that's it. And then adjust the format a little bit so to make it look nicer. Okay, so that's it. That's our first module, the full adder module. Okay, save. Okay, so our goal is to implement a 16-bit version full adder, but instead of putting 16 full adder instances in this REPL adder module, we're gonna build a 4-bit module, and we're gonna combine the 4-bit full adders to make a 16-bit adder. So we're gonna do this module 4-bit RA. RA stands for REPL adder. So again, input and output list. Again, these parentheses don't have to be aligned with each other. It's just my own habit. Input, which is going to be a 4-bit stuff. So 320. So that's 4-bit X. And then input 320 Y. So this basically declare a data type that has 4-bit. And then input carry in, because we're going to need a carry in. Oops, sorry, these are not semicolons, but commas. Then output logic 320 S. And finally a carry out bit logic C out. So it looks pretty similar to this one below, but there are just more bits in the input and output. So in SystemVerilog, we don't actually call another module. The terminology we're going to use is instantiate. So we're going to put four full adder instances. Full adder fa0. I'm just going to make one and copy it 4 times. So here inside this parenthesis, we're going to match the input at this level with logics at this level and output as well. So we're going to do dot x. So this dot x actually refers to the x here, not this one. Although they have the same name, but they belong to different hierarchy. So dot x is the 0th bit of x here, so x0. And then dot y is the 0th bit of y, so I get y. And then cin is just the cin. Then s would be s0. Okay. Then the C out. Oops, what C out should this be? So because this C out can't just simply connect to this C out, so we have to declare some internal logic inside this hierarchy. So we declare logic C, okay, let's call it C0. And we're gonna have, I guess, 3 of them. So C0, C1, and C2. What's C3? C3 is this C out itself. So we're gonna do C out, go with C0. That's it. And we're gonna copy this line three times. So, and change the subscripts. We're going to do, this is 1, 2, 3, 1, 2, 3, 1, 2, 3, and so the C in here is obviously the C out from the previous full adder. So this is C0, and this will be C1, C2, and here it will be C1, C2, and finally the overall C out. So let's match the parentheses. It's a bit clear. Okay, and that's it. That's our 4-bit ripple carry adder module. Now we're gonna put 4-bit RA to make one 16-bit RA. Again, we are gonna need some intermediate values. So we're gonna need logic C. To distinguish, let's call it capital C0, C1, and C2. And then what we're going to do is put this here. By the way, in order to distinguish them, you have to give it a name. So let's call it 4RA0. F stands for 4. Now we're going to, again, put the dot x. This x gets, okay, I guess it will be A320, right? Because this 4-bit will correspond to the leftmost 4-bit here, and so on. And then y is B320 parentheses, and what else? We have C in. We're just, because we're only performing adding, so we'll just put 0 here. And next, S, which is the sum 320, and C out. We have already done that. C out is this C0. Okay. And again, we're going to copy paste this 3 times. Change the subscript. I'm going to jump ahead a little bit here. Okay, so guys, I just realized that I made a very bad choice of the subscript here. So C0 and C out, they look pretty similar, but pay attention, this one is the capital O. So this is the final C out, and this is C0, which is the carry out of the FRA0 4-bit ripple carrier adder module. So just don't get mixed. Okay, that's it. That's our 16-bit ripple carrier adder implementation. It's pretty neat because we have used this hierarchical design. We have the 1-bit module, have the 4-bit ripple carrier adder module, and we put together 4 of them to make a 16-bit module, which is pretty neat. So you guys should also do this hierarchical design instead of putting 16 of those full adder. Here we call it flat design. It's really confusing and it's a really bad practice. Okay, so now we save our files. Next, what do we do? Oh, we want to test it, right? So we have instantiated everything here. Now we need a test bench. So a test bench is basically a script written in SystemVerilog, which cannot be synthesized and compiled onto the FPGA, but you can use that to check whether your circuit is working or not. Okay, so let's create our own test bench. SystemVerilog SystemVerilog HDL. Okay, can I change the name of it? I guess I can't. So now we're going to write a most basic test bench. We're going to call it module. So test bench is also a module. We're going to call it test bench. Basically, it has no input and output because it's the final. It's even on top of the top level. You have to put your top level inside the test bench. So this guy has no input and output. We're going to define our time unit to be 10 nanosecond because we're using a 50 megahertz FPGA. So the minimum time unit would be 10 nanosecond. One down and one up takes 20 nanoseconds. So in time precision to be 1 nanosecond. So that's the resolution. And then we're going to declare some logic. So what do we put as the internal logic of the test bench? Of course, is the input and output of the top level, because we're gonna put the top level inside of the test bench. So the input and output of the top level naturally becomes the internal logic of the test bench. So we're gonna change the commas to semicolon. We're gonna do this. Place all. Anyway, and next, we're going to define the clock. So we're going to use always begin. By the way, so always is an old Verilog syntax, and we're going to name this procedure block clock generation. Then #1 means after every 1 time unit, meaning every 10 nanosecond, we're gonna toggle the clock. Clock equals to not clock. So this toggles the clock and this block. This delay here is not synthesizable, so you cannot expect your hardware to really make a delay and then execute something. This syntax is only for test bench purpose. And then we do an initial block. Initial is also a procedure block which will execute once at the startup of this whole test bench, but always block will always be like will always execute. So it will be repeating clock so it will be repeating and generate the clock up and down, up and down, up and down, so on. So at the beginning, we define the clock to be 0, or actually whatever you want. And then we're gonna put our oh, by the way, let's name it clock initialization. And next we're going to put our top level here. What's the name of it? It's called Lab4. Adders top level. So let's call it TP. And then for the input and output list, we just call dot star because we copy those names verbatim from here. So for those who has the same name, they will automatically match. But you have to pay attention to this notation, because if inside your top level you accidentally have some logic that, for example, has the name SW but not necessarily switch, you just name something else as SW, it will match with this SW here. So it will refer those by name. So just pay attention. Unless you really want to like pair them up by name, you should do something like this. So pair them by hand, but it's okay to do it here. Okay, now I have renamed the test bench SV. And finally, we're going to jump into the main body of our test bench, which is called the test vector. It's also an initial block, so it will execute once sequentially. Begin, let's go with test vectors. Test vectors, by the way, you can actually name it whatever you want, but just make sure those names are informative. So at the beginning, we're going to set the reset to be 0, right? And the load B to be 1, because when we're doing the demo, we'll do these things physically on our FPGA board. Run. So let's do a test case. By the way, you can add comments like how you do it in C. Test case 1. So after 2 time unit delay, we're gonna set the reset to be 1. So basically, all the buttons, as you can see here, at this corner of the DE2 board, are active low, meaning when you press them, they are in logic 0. When you release them, they are in logic high. So 0 here means I want to reset, and 1 here means I don't want to reset now. I'm not pressing the button. So, and after another 2 time unit, we're going to toggle load B to be 0, and we're going to make our switch to be 16 hex. So basically, I'm gonna input a 16-bit wide in hex format, so 0001. So this is really equal to 16 in binary 0000000000000001. But it's just stupid to do that. So now we're going to change load B to be 1. So now we're actually loading A. Here we're loading B, and these 2 lines happen simultaneously. Now we're going to load. And here, because it's active low, setting load B. And here, because it is active low, setting load B to 1, meaning we don't want load B. We want to load the value into A. So we're going to do similar stuff. We're going to do, let's do this. And then run equals to 0, starts running. And sorry, after 2. So, and let's wait for a couple of time unit, say 20 or whatever. Okay, and we end this initial block. And finally, we also want to end the test bench module. Okay, so everything looks all right. We're going to click on this. So this is the compile, but it will generate everything that you need to program your circuit onto the FPGA. We don't need to use it right now. We just click on the analysis, which saves us. We just click on the analysis button, which will save us a lot of time. So we're gonna, oops, I didn't specify the top level yet. So let's do that again. We're going to specify a top level. It is this. So we say set as top level entity. And also we have to specify our test bench file. So we go to assignment setting, simulation, make sure it is Model Simatera, then compile the test bench as well. We're going to select the test bench. Test bench is named test bench. Make sure it has the same name as you put on the module. Then we're going to add a file. We're going to simulate this in let's say 1,000 nanosecond, and we're going to add file. So we go to our simulation file here, testbench.sv, add, okay, apply, okay. Now we can start the analysis. It takes a while. Oops, look like we have got some bugs we have to fix. So we click on this, and this leads us to the end. What's happening here? So it said near the text end, expect this thing. So let's check. So we have semicolons everywhere. If we're gonna do nothing, I think it requires a semicolon here. So let's do that again. Oops, even more errors. So we're gonna fix them one by one. Not found in the port list. Oh, right, because when I copy them, I forget to delete the input because they are internal logic. They don't want to be named input or output. So let's do that. By the way, if you want to select a row, you want to select a column instead of a row, you can press Alt when you're doing the selection. Then, okay, let's do that again. Okay, let's just debug one by one. Object load B is not declared. Okay, so I guess we have to declare the signal load B as an internal signal. Or am I doing something stupid? Because load B is here. What's happening? Not declared. Verify if the name is correct. So, ooh, see, it's different. What's happening? Oh, I'm typing lobe B, so that's why. Fix this error. Continue. Okay, so now the analysis is done. We're gonna open up the model simulation tool. It's in tool, run simulation tool, RTL. Pay attention, don't press the gate level simulation. It's really slow. It's more precise, but it's just slow. So we're going to do the RTL simulation. So the simulation will be finished at the register transfer level. Okay, the model sim is here. So basically this is our circuit. This is the waveform. Okay, let's zoom out a little bit. So you can see at the beginning there is no, these are not specified. They are unconnected, but we don't care about them now. Can we zoom out further? Okay, now we can see the entire waveform. As the test bench says, we're gonna toggle the input here. We're gonna set the switch at this level and hit run. So basically this just reflects our test bench content. So you can see when load B is 0, our input is switch is 1, so that loads 1 into B, and when this is high, we load 2. Basically, binary 1, 0 is 2 into A, and then we hit run at this moment. So run becomes 0, and after a while we can see, okay, the output is here. 1, 1 is decimal 3. So our circuit is successful, and let's look at the carry out. It's 0, and it is also correct. Okay, that's it. That's all for your very first SystemVerilog lesson. I hope you guys enjoyed this video, and I hope you learn from it. The other two adders are basically similar, although they are more complex in terms of structure, but you just follow the procedure and write your own test bench. That's it. Thumbs if you like it. Once again, I'm Yi Quan Chen, and I will see you guys on KT Tech and the Open Labs.